Welcome everyone, welcome back to today's session. And today we are having the final session for quantum machine learning with Fraunhofer. If you are joining in just today, I would recommend scrolling back through the YouTube recordings and the YouTube playlist to watch all the preceding quantum machine learning sessions. They are in sync with what has already been discussed. And beyond that, today we are starting with a brand new topic about introduction to ZX calculus. Ivica is here with us today from Fraunhofer ITWM. Ivica, over to you. Could you do a quick introduction and then the stage is all yours.
Thank you very much, Vardaan. So my name is Ivica Turkalj. I'm working at the Fraunhofer ITWM. This is a German research institute for applied mathematics. And my academic background, I have done my PhD in pure mathematics, so in number theory and algebra, to be precise. And after that, I moved to the insurance industry. I worked for 4 years, I think, with a German insurance company as an actuary. And then I learned that there are a lot of different connections between financial applications and quantum computing. So I make the switch to research again, and now I'm doing research with Fraunhofer ITWM on various topics on quantum computing. So we are looking into machine learning applications or just general algorithmic development for different applications in finance, like risk measures or some regulatory topics which are important in Europe. And also we have looked recently into ZX calculus, which is, maybe it's not familiar to every one of you. It's a little bit more abstract, but even this abstract things have nice applications into finance. So yeah, let me start with my presentation. So today's topic, it looks more closely at the fundamentals of quantum information science. So during the last weeks, you first received an introduction to quantum computing, where all the basics, such as qubits and unitaries and all this stuff, were explained. And then more in-depth topics were covered. So where you basically went through different sub-areas of quantum computing, like a little bit more hardware, a little bit more AI. Today, I'm going to cycle back to the basics, but with an interesting twist that will give a new perspective on the whole subject. So, and this twist is called ZX calculus. And before I start with the technical details, let me try to give you the big picture of what ZX calculus is all about. So the big picture goal can be phrased pretty much in one sentence. ZX calculus is a new mathematical description of quantum computing and quantum information theory. So it is really a new mathematical formalism that uses different kind of math objects to reason about quantum theory. And the introduction into this mathematical description will be the main goal of today's talk. And I admit the phrase mathematical description is somewhat vague, so let me briefly repeat the key points of the formalism of quantum mechanics that you learned so far, but without going too much into detail, just to remind you of some terminology. And so everyone who learns quantum theory for the first time starts with the Hilbert space model. And to do stuff in this model means to work with math objects like complex vector spaces. And in these vector spaces, you have different kinds of multiplication. You have tensor products and inner products. And this whole structure allows you to build more interesting objects like orthonormal bases and finally quantum states. And designing quantum algorithms and quantum protocols is done by applying certain transformations to these objects. And all these transformations that you will encounter most often in Hilbert space model are various types of linear maps. So for example, you have unitaries, you have Hermitians, you have orthogonal projectors to model the measurement process, you have the trace and the partial trace to look into subsystems of bigger quantum systems. yeah, so this is the basic mathematical structure of the Hilbert space model. And now, on the other hand, the new model works quite differently. It's built, so its basic building blocks can be thought of as graphs. So no complex vector spaces anymore, just graphs in the sense of graph theory. And designing algorithms in this model is done by applying certain rewrite rules to these graphs. And these rewrite rules are more formally axioms, which describe little equalities between different graphs. So this, I mean, it's basically a completely new way of working with quantum theory. And it was indeed possible to show that the Hilbert space model and this new model are equivalent. So this means both models are equally powerful in describing what's going on in quantum theory. So later we will state this equivalence result more precisely and also explain what is meant by saying that two models are equivalent. Here I just wanted to show you the big picture and what you can expect from this description. And now, before diving into technical stuff, let me give you some hints why you should be interested in this alternative way of describing quantum processes. So first of all, a very straightforward reason to get familiar with ZX calculus is that it has become a widely used tool in research. So it started out as a very abstract thing. So the initial aim was to describe quantum mechanics in the language of category theory, which is a very abstract math theory, even for mathematicians. And from this very abstract initial version, a theory has developed over time that has many applications. So, for example, it is used for design of error correcting codes, which is an important topic, obviously. And recently, it has been applied in quantum machine learning, where it is used to investigate how gradients of parameterized circuits can be evaluated directly on quantum hardware. A somewhat more traditional application is circuit optimization. Here, the goal is to reformulate a given quantum circuit so that it satisfies special constraints that are important for the user. So, for example, to minimize the use of an expensive gate or something. And photonic quantum computing is a traditional field of applications. This is mainly due to the fact that photonic quantum computing uses the so-called one-way quantum computing model or measurement-based quantum computing, which is another different model, different from the circuit model, but which can be expressed very easily with ZX calculus. And we at Fraunhofer have used ZX calculus to perform quantum architecture search. This is a subfield of quantum machine learning in which you not only try to find parameters of a quantum algorithm to reproduce some data, but the structure of the whole circuit is subject to the learning procedure. Yeah, so ZX calculus has become quite established, and this is just a small selection. In reality, there are many more interesting applications. And so I would like to give you one more reason why you should take a closer look at ZX calculus. And from my personal perspective, this is probably the most important reason to look into this topic. And yeah, this might sound like an obvious statement, but everyone has experienced that. Following a solution to a problem is much easier than coming up with a solution yourself. I mean, as a student at university, you have this feeling probably with every homework assignment. So, so my point is, it's very valuable to have something that is supporting you in finding the solution to a problem. And ZX calculus does a really good job at it. So all quantum algorithms and all quantum protocols use all these non-intuitive quantum properties like superposition and entanglement. And if you're working in the Hilbert space model and you have a quantum circuit in front of you, I mean, then it's often relatively easy to see that the algorithm does what it promises. I mean, you only have to multiply matrices at the end of the day. But it's incredibly difficult to find the solution if you only think in terms of matrices. And the benefit of ZX calculus is that it translates the non-intuitive quantum properties into geometric properties of graphs that are more accessible to our intuition. Yeah, and for me, this is the real strength of ZX calculus. So, all right, let's start with the construction. So when you see the construction of ZX calculus for the first time and you have no experience with more abstract concepts like mathematical logic or formal languages, then the individual construction steps will seem a little bit arbitrary. So I would like to outline what the general workflow looks like if you want to introduce a new formalism for an already existing theory. And I'm only describing the general procedure here, so that it's easier to understand what's going on during the construction of the ZX calculus. So the first step is to define your notation. So here you define the symbols you are going to work with, and you define how to combine these symbols into new symbols. And the technical term for this is you define the syntax for your formalism. And so only have new symbols. I mean, at this point, the defined symbols are not yet related to the theory for which you are trying to construct the new formalism. And the connection to the existing theory is called semantics. Here it is necessary to define precisely how the symbols introduced are related to the mathematical objects of your theory. So in this step, the abstract symbols are given a meaning in the context you are actually interested in. So for us, this would be the Hilbert space model. And now, if you were to stop at this point, I mean, you would only have introduced a new notation for an old theory. So to get something new and helpful out of this construction, you have to introduce an axiomatic system for the new syntax. And an axiomatic system is a set of equalities which by definition are true in your new syntax. And finally, this whole thing together, so like the axiomatic system and the new notation, it defines our new theory, and via the semantics, we can determine how much of the old theory has been captured by the new formalism. Yeah, and the goal is to choose your symbols and your axioms in such a way that you can reproduce as much of your old theory as possible. And what you have achieved at the end is that you will have a new and hopefully better way to think about questions you care about. I know this sounds a little bit abstract at the moment, but we will see it in action soon, and then things will become much clearer. So with this slide, I just wanted to explain why the following construction is not just an arbitrary collection of symbols and calculation rules, but that is exactly how new theories are modeled in mathematical logic. Yeah, so let's start with the first step of our construction. So our basic symbols will consist of small graphs, like this one on the slide. But we do not allow arbitrary graphs. The graphs that we allow as our symbols must fulfill certain conditions. And I will briefly go through the properties so that we can see what really matters in these two images. So these graphs must consist of exactly one vertex. And this one vertex must be colored, either green or red. And the vertex must be labeled with a real number. And there may be any, but only finitely many number of edges. This is indicated by the natural number n and m of both sides. And what is also important, the edges may be open, which means they do not have to be connected to other vertices. So the edges on the left-hand side of the vertex are called input wires, and the edges on the right-hand side are called output wires. And these small one vertex graphs are called spiders because they look a little bit like spiders. Yeah, and these spiders will be the language we will use to talk about quantum theory. So to make the connection to quantum theory, we need to say something about the semantics. And the exact interpretation of spiders in the Hilbert space model is shown here in the formula. The basic idea is to interpret spiders as linear maps on Hilbert spaces. So green spiders correspond to linear maps that arise by looking at the computational basis. And red spiders correspond to linear maps that arise by looking at the plus-minus basis. Yeah, and of course, each property of a spider is somehow related to this linear map. So the number of input and output edges determines the dimension of the vector space between which the linear map operates. And the label of the vertex defines the relative phase. And one important remark here, it is not required that the linear map is unitary. So in general, this cannot be the case simply because of the potentially unequal dimensions of input and output domain. So spiders correspond in general to arbitrary linear maps. Yeah, and these spiders are kind of the basic alphabet for our new language. But the definition of a syntax also includes specifying how new symbols can be combined from the basic alphabet. And that's what we're looking at next. We will define two ways in which spiders can be combined. So these two ways correspond to the two ways of multiplying matrices in the Hilbert space model. So one way is just the ordinary matrix multiplication, and the other is by tensoring or by the Kronecker product. And we start with the so-called sequential operation on spiders. So suppose we have two spiders of any color. For example, I have now taken two spiders of different colors, but the operation applies between spiders of any color. And by the way, the black frame around the spider has no mathematical meaning. It's just to indicate where a spider starts and where it ends. So just to minimize misunderstandings. And the sequential operation is now simply consisting of connecting the output wires of the left spider to the input wires of the right spider. And yeah, you have to be a little bit careful because this only makes sense if the number of output wires is equal to the number of input wires, which, by the way, fits very naturally with the interpretation in the Hilbert space model. The semantics of this operation is the composition of linear maps, or in matrix form, the multiplication of matrices, and matrix multiplication as an analogous condition. So two matrices can only be multiplied if the number of columns in one matrix is equal to the number of rows in the other matrix. So this is completely analogous here. The next operation corresponds to tensoring. So when working with tensor products, it will become clear how much more natural this two-dimensional notation with spiders is compared to the usual linear algebra notation. So again, we start with two arbitrary spiders and define the parallel operation simply by placing two spiders on top of each other. So here I find the black frame useful because it indicates that stacking two spiders has really created a new diagram. And this new diagram has both inputs of the first spider and the second spider as its own new inputs. Yeah, regarding the semantics of this operation, it consists of, yeah, as I said, of tensoring two linear maps, or in matrix form, the Kronecker product of two matrices. And I mean, if you look at the red box on the right side, and you look at the formula on the bottom, I think one can already see that this at this point how much more natural the spider notation appears in comparison to the Hilbert space notation. So we have two different concepts of multiplication, and which makes writing formulas and ultimately thinking about relations between these objects a bit complicated in the Hilbert space model. So the spider notation is much more well suited for working with tensor products and in multiplication. Yeah, and now by combining different spiders in sequence or in parallel, one can construct all possible kinds of diagrams. So for each of these diagrams, one has a well-defined interpretation in the Hilbert space, namely as a linear map. So that is what a general ZX diagram looks like. So again, the black frame is usually not printed, but it makes it easier to determine on which vector spaces the linear map operates. So here you can see by looking how much wires go out on the left side, you see that the linear map operates on 5 qubits, and it has an outputs 3 qubits. So this is something which isn't even possible to write down in the circuit model, because the input wire, the number of input wire is every time equal to the number of output wires. But here you have more freedom. And in principle, ZX diagrams can be read in a similar way to quantum circuits. As with circuits, you read the diagram from left to right, and just as you divide circuits into layers, you can divide the diagram into individual columns. And the individual columns are combined by matrix multiplication, and each individual column is created by dividing the column into smaller parts, which are then combined using tensor product. Yeah, and by the way, in this picture, we have already used a few of the usual simplifications in the notation that are common in the literature. So spiders with phase 0 are written without any parameter. And the 0 spider with exactly one input and one output corresponds to the 2 times 2 identity matrix and is denoted as a continuous wire without spider. So it's just a plain wire. And before continuing with the construction, so we have now constructed the syntax and the semantics. The next step would be the axiomatic system. But before we look at the axiomatic system, let's take a step back and see how much of the good old Hilbert space model we can already capture with this little spider notation. So one thing you might notice is that so far we haven't talked about vectors at all. So our spiders are translated into linear maps. But of course, ordinary vectors play an important role in quantum theory because they describe the state of quantum systems. So how can we represent ordinary vectors in our new model? And so quantum states are indeed representable as ZX diagrams, but to see this, you have to read the definition of a spider very carefully. So if you recall the definition, so here on the top right, a spider is a one vertex graph where the number of input and output wires can be any natural number. So in particular, the natural number 0 is allowed. And if we set the number of input wires to 0 and simply apply the definition on the right-hand side, you actually end up with a quantum state. So for example here, if our red spider has 0 inputs and 1 output, and we set the phase to 0, then we get the ket 0 state. And if you want to be very precise, we would always have to pay attention to whether we need to consider a scalar factor. But in most applications, the scalar factor does not play an important role. And if necessary, we can always find out the correct factor at the end of the calculation and add it to the diagram. So we will always ignore the factor in the following. Yeah, and to continue with the example, if we choose the phase as pi and not 0, we get the ket 1 state. And if we do the analog calculation for the green spider, we end up with a plus-minus state. And yeah, so here you have to choose the same phases again, but you end up with the different bases. Another very important quantum state is the belt state. So probably the most important one. Remember, the belt state is the equal superposition of ket0 and ket1 in a two-qubit system. And again, if you look at the definition, the belt state corresponds to the spider with 0 inputs and 2 outputs and with phase 0. And because the belt state occurs so frequently, a specific notation has been introduced for it. It is written in the ZX calculus as a bent wire without any spider. And finally, the conjugate transposed version of the belt state is also frequently used, and this spider is called the bell effect. And here the notation is just a wire used that is bent in the opposite direction. So now we have seen a few important quantum states that can be expressed in the ZX calculus. How about unitaries? So let's investigate whether the more familiar unitaries from quantum computing can be represented as ZX diagrams. The Pauli Z and the Pauli X matrix are name-giving for the ZX calculus, so you would definitely expect that they have a simple representation by spiders. And indeed, they have a very simple representation. It's just a pi spider with one input and one output. The most important single qubit unitary, the Hadamard gate, has a little bit more complicated diagram. So the idea of the diagrammatic representation of the Hadamard gate is to use Euler angles to decompose the gate into 3 rotations. And this decomposition in rotation is very simple because it only uses 90-degree rotation angles. So you can write the Hadamard gate as a sequential product of 3 spiders with phase pi halves. Yeah, and as a side note, in the literature, it is common to denote the Hadamard gate by a yellow box. It's just a simplified notation because the Hadamard gate appears so frequently, it would be too annoying to write out the Euler product every time. So yeah, this is just a new symbol for the product of 3 spiders. The CNOT gate has the following matrix representation in the computational basis. And in the ZX calculus, this matrix can be written as a diagram with 2 spiders. And maybe this is not so easy to see by simply looking at the definition, but you can convince yourself of this equality by comparing the operation of these 2 maps on the computational basis. So because for 2 linear maps to be equal, it is sufficient that they coincide on a basis, and this can easily be checked. And it is also worth mentioning that it does not matter whether the green or the red spider comes first in the diagram. So this justifies the symmetrical notation for the CNOT gate. And in fact, the trick we use for the Hadamard gate, such an Euler decomposition exists not only for the Hadamard gate, but for every 1 qubit unitary. So this was probably mentioned in one of the previous lectures, but if not, this is a well-known result that can be found in any textbook on quantum computing. So here is the exact formulation of the theorem. For any 1 qubit unitary, you can find 3 real numbers, alpha, beta, gamma, such that the unitary operator can be decomposed into the corresponding rotations with angles alpha, beta, gamma. But this immediately implies a representation by spiders, because just like with the Hadamard gate, you can write an Euler decomposition as a sequential product of 3 spiders. You just have to make sure that you choose the phases of the spider appropriate to the angles of the rotation. And this line of argumentation can be taken one step further. So on the last slide, we saw that the CNOT gate can be written as a ZX diagram. And this theorem states that every 1-qubit unitary can be written as an ZX diagram. Now, another well-known theorem from quantum computing states that any unitary matrix, not only 1-qubit unitaries, but any unitary on any number of qubits, can be decomposed in terms of matrix multiplication and tensor products into 1-qubit unitaries and CNOTs. So this means that by being able to write the CNOT and the 1-qubit gate as an ZX diagram, we have shown that every unitary can be written as an ZX diagram. So this little diagrammatic notation already captures a large part of what is important in quantum theory. And that is already pretty useful, but we can go one step further. So not only every unitary can be written as an ZX diagram, but every linear map between qubits can be represented as a ZX diagram. And this is known in the literature as the universality theorem. And that is a first indication that the ZX calculus can be very powerful, and it already indicates where exactly the power comes from. So what I mean by this is this expressiveness allows linear objects to be broken down further than it would be possible in the Hilbert space model. So we have already seen this in the CNOT example. So in ZX calculus, the CNOT gate can be decomposed into 2 spiders, whereas in the usual quantum circuit model, the CNOT gate cannot be further decomposed. But if you can decompose the CNOT into smaller parts, then these individual parts can interact with other diagrams, so that sometimes a conclusion is possible that would not be possible with ordinary quantum circuits. It's a little bit like going on a little detour. So you are actually interested in unitary operators, but you deliberately take a little detour via the set of arbitrary linear maps because you might be able to pick up something there that can help you reason about unitaries. And by the way, this is fairly common strategy in pure mathematics to solve difficult problems. So I did my PhD in number theory, and in algebraic number theory, you actually do something similar. So if you're interested in statements about ordinary integers, then a common strategy is to look at the same statement, but in a larger domain of numbers. And these larger domain of numbers are called number fields. And it often turns out that you can perform transformations in these number fields that are not possible in the ordinary integers, but which then still essentially contribute to solving the problem in the ordinary integers. So this is exactly what's happening here in the ZX calculus. Yeah, so let us prove this theorem, or at least give a sketch of the proof. So let's imagine the linear map that we want to decompose into spiders as a diagram. So it is not a formal ZX diagram because it doesn't consist of spiders. It's just a simplified notation for capital F. And there's a natural way to translate a linear map into an ordinary vector. So this is called the Choi-Chermykovsky isomorphism. And the somewhat informal description of this transformation is given in the following diagram. So what has happened here is that the linear map is composed with several belt states, and the belt states transform the inputs to outputs. And as we have already seen with the zero input spider, linear maps without inputs can be considered as vectors. And without loss of generality, we can assume that the vector has length 1, meaning it describes a quantum state. But every quantum state can be reached by applying an appropriate unitary to the ket0 state. So this follows from basic linear algebra. So the quantum state phi can be extended to an orthonormal basis, and 2 orthonormal bases can be transformed into each other by a unitary. And now we are in the situation that we consider a product of a unitary with the ket0, and the fact that U can be written as an ZX diagram follows from the theorem on the last slide. And we saw that the ket0 can be written as a ZX diagram when we looked at how to write quantum states with spiders. So it follows that the whole diagram on the left-hand side with capital F at the top can be written with spiders. But from this bent diagram, we can reconstruct the original F by applying bell effects to the bottom. So the bent virus, so we bent the virus back to the original position, so to speak. But this bending process is just, again, the bell effect, which we have seen can also be written with spiders. So since every single part can be written as an ZX diagram, in the end, the whole F can be written as an ZX diagram. So this is roughly the idea of the proof. You use the Choi-Chmielkowski isomorphism to translate linear maps into quantum states, and then use universality results for unitaries. So these were some first examples and first theorems. Let us summarize again, once again, the steps we have completed in the general construction of the theory. So we have defined the syntax in the form of spiders and in the form of sequential and parallel composition. We have defined the semantics by clarifying the relationship between spiders and linear maps. And what is still missing is the construction of the axiomatic system. That's what we're going to address next. And the axiomatic system will consist of a small set of calculation rules that apply to small spider diagrams. And once we have introduced all the axioms, we will take a look at how powerful the new theory has actually become. So we start with the spider fusion rule. So this rule says that when two green spiders are connected by some wires, then you can fuse these two spiders together. And their phases behave as if two rotations were carried out one after another, so the angles add up. And this rule applies to every possible number of input and output wires and to every possible number of connecting wires. So in applications, this rule is often used from right to left. So you unfuse spider to enable the application of other rules that we will discuss next. Yeah, on this slide, we introduced two axioms that can be understood as ways of copying spiders. The first rule states that you can push a red spider through a green spider, thereby destroying the green spider and leaving copies of the red spider. And the number of red clones you are left with corresponds to the number of output wires the green spider had. And the second cloning rule says that you can not only copy spiders that represent quantum states, as in the first case, but also spiders that represent unitaries. So the difference in the second rule is that the copied spider has an input wire, whereas in the first case, the red spider had 0 input wires. And the difference in the result is that the green spider is not destroyed during cloning. It only has to change the sign of its face. And from a slightly higher perspective, so whereas the cloning of quantum states in the usual Hilbert space model is very restricted by the no cloning theorem, in ZX calculus, you have a little more freedom, which is ultimately due to the possibility of making small detours for the set of non-unitary matrices. Now the following three axioms I have grouped together because they reminded me of small rules from group theory. But this is just a silly name I made up. It's not terminology you will find in the literature. So the first axiom on this slide states that the green phase 0 spider behaves like the neutral element with respect to the sequential composition. So one green dot with one input and one output wire is equivalent to the identity operation. And the second axiom states that the Hadamard diagram is inverse to itself with respect to sequential composition. So if you remember, we have denoted the Hadamard gate by this yellow box. And the third axiom is called color change rule because it says that you have to change the color of a spider if you put a Hadamard box on each wire. And this is so why I associate this rule to group theory is because the rule expresses a conjugation rule. In group theory, one speaks of conjugation when an object is sandwiched between group elements and its inverse. And this is exactly what's happening here with the color change rule. So a spider that is sandwiched by Hadamard is again a spider, but with a different color. And so far, all these axioms have been relatively intuitive. So spider fusion and copying is easy to memorize, and the rules on the last slide are also pretty intuitive. The second last axiom, which we will look at, seems a little bit more complicated at first glance. It says that diagrams that form this kind of square on the left side can be simplified in this manner. And in order to really understand and appreciate this rule, you need to look a little more closely at the origins of ZX calculus, which is category theory. And this is beyond the scope of this introduction, but you can think of this rule. You can think of that this rule expresses that the Pauli Z and the Pauli X operator are strongly complementary observables. And this strongly complementary property is really what distinguishes quantum world from the classical world. It means that in the quantum setting, there exist two physical properties which are unknowable at the same time. So if you are in the eigenstate of the Z observable, then you have maximal uncertainty regarding the eigenvectors of the X observable. And this axiom is the diagrammatic encoding of this property. And the last axiom is again about something intuitive. It says that under certain conditions on the angles, two Euler decompositions are equal. So yeah, that was a lot of rules to absorb in a short amount of time, but if you honestly compare that with the Hilbert space model, and if you consider how much mathematics you have to develop to even get started with Hilbert spaces, so I mean, you have to develop almost whole of linear algebra, and in the infinite dimensional case, a large amount of functional analysis. And in comparison, this axiomatic system of ZX calculus is quite compact. And yeah, so before we continue, one important note, all axioms remain, so on the left side, all axioms are summarized again, and all axioms remain valid if you swap the colors of the spiders involved. So this follows from the color change rule. And I just wanted to mention it at this point. So an interesting question that naturally arises is how powerful is this axiomatic system? So because ZX calculus can only be regarded as an adequate replacement for the Hilbert space model if the same theorems can be proven in the axiomatic system as in the Hilbert space model. And I would like to show you two theorems that addresses this question. So the first theorem relates to the so-called soundness property. And it states that any equation between ZX diagrams, which is obtained by applying these axioms, also yields an equality between the induced linear maps. So this means more informally that whatever insight about quantum theory you gain by working in the ZX calculus, that insight will remain correct in the Hilbert space model. And that is a cool theorem, and it's not that difficult to prove. But I think I have only a sketch of the proof, which consists of simply checking that each axiom remains a true statement about linear maps in the Hilbert space model. And to extend this property to whole diagrams, you have to check that these qualities are compatible with the composition rules for ZX diagrams. That's not that difficult. But a more difficult result is the following. So not only do true statements in ZX calculus remain true when translating into the Hilbert space model. In fact, the opposite direction is also true. So every true statement about linear maps on qubits can be proven by applying these 8 axioms from ZX calculus. And this is called the completeness property of ZX calculus. And this result is truly amazing because it says everything that can be learned about quantum processes can be deduced by looking at these little small rules of ZX calculus. So every quantum algorithm, every crazy quantum protocol, everything we care about in quantum computing and quantum information theory is already present and waits to be discovered in this little cute calculation rules. And I find this really amazing, and this result was really a surprise for the ZX community. I think the initial developers didn't really anticipate this result. So the proof is really difficult and deep, and its discovery was really, really surprising. And so after we have discussed some theoretic results, I would like to show you what you can do with ZX calculus in practice. And we will look at the quantum teleportation protocol and how to derive it in the ZX calculus. But to get started, let's begin with something simple to get used to applying these calculation rules. So let's use the formalism to show that the ZX version of the CNOT gate behaves exactly as you would expect a CNOT gate to behave. So it's not a deep result. It's just to show you how you can combine these small rules to prove stuff. So what we have to show is that this diagram behaves exactly like the ZX, like the CNOT gate, which means if you plug in the 0 cat to the control qubit, you end up with the identity. And if you plug in the cat1 qubit into the control qubit, you end up with copying the state. So let's start with the first case. So in inserting cat0 into the control qubit produces the following diagram. And if you now look at the axioms and think about which of these rules you could apply, then the only real option is the copy rule. So here at the bottom, 2 spiders are now connected, which have the same color. So you can merge them with the spider fusion rule. And a spider at the bottom without phase and with only one input and one output is the identity. This is axiom ID. So yeah, we arrive at the diagram with cat0 on the control qubit and the identity on the target qubit, which is exactly what the CNOT gate would do. And now for the second case, here we plug in cat1 in the control qubit. And if you remember, the cat1 state is this red spider with pi as a phase. And at first you might think that pi copying is a good idea, but the pi copy axiom is not applicable here because the pi spider has 0 inputs. But here you can use a little trick, which is often used in ZX calculus. You use the spider fusion rule from right to left. So you unfuse the spider to make the copy rule applicable. So if you do this here, you end up in a situation where the pi copy is now applicable. And the pi copy axiom produces the following diagram. And the bottom 2 red spiders can be fused again. and you get in a situation where now the ordinary copy rule can be applied at the top. And you get now again in the situation where you can apply the spider fusion rule twice. And at the end, you get a diagram in which the cat1 from the control qubit appears on the target qubit and with corresponding and the cat0 also appears on the target qubit and control qubit. So you have copied the pi state, the cat1 state as the CNAT operation would do. So this is just an example to warm up and to demonstrate how small theorems from the Hilbert space model can be easily proven in the ZX calculus. So to conclude, let's look at the more significant example. So let's look at the quantum teleportation protocol. Here is the usual description of quantum teleportation in the circuit model. And as a reminder, in this protocol, there are two, Alice and Bob. And the assumption in this protocol is that Alice and Bob share a common Bell state. So a 2-qubit system is prepared in a Bell state. And 1 qubit of this 2-qubit system is with Alice, and the other qubit is with Bob. And a part of this 1 qubit that is shared, Alice also has access to a second qubit, which is shown in the picture at the top. And she would like to somehow transfer the state of the upper qubit to Bob. So this is the goal of the protocol. I mean, but yeah, so but she can just hand over the top qubit to Bob because let's assume Bob is far away in another galaxy. And in the previous lectures, you have already seen that this quantum circuit allows to teleport the qubit of Alice, provided that 2 classical bits of information may be communicated. So Alice must send Bob the result of her 2 measurements. Now let's prove in ZX calculus that this really does the job. So first of all, fit the circuit into a ZX calculus, and it provides this diagram. So we simply replaced. So if you compare these 2 diagrams, we simply replaced every gate in the circuit model with the corresponding spider in the ZX diagram. And so the measurement can be represented by this 0 input, 1 output spider. And in the quantum circuit description, there is this dependency between the measurement result of Alice and what Bob does with his qubit. This is indicated here with this double dash lines. But in the ZX diagram, we have realized this dependency by introducing 2 Boolean variables, A and B, which ensure that Bob takes its action depending on the measurement result. So A and B can take the values 0 and 1, and depending on whether 0 or 1 is realized, and Bob will take the corresponding action. So which axioms are now applicable? So at the top, we see 2 red spiders are connected. So you can use spider fusion. Now, if you look at the Hadamard gate, the color change rule can be applied to the Hadamard and its red neighbor. So you end up with 3 connected green spiders, which can be fused. Now let's look at the phase of the green spider. So in the phase, the Boolean variable B appears, which is either 0 or 1. But in both cases, regardless of whether B is 0 or 1, the phase will be an integer multiple, which is equivalent to phase 0. And yeah, phase 0 spider is just the identity, so it can be removed. And the 2 red spiders can again be fused, and you have another spider which has a phase which is always a multiple of 2 pi. So it reduces to the identity. Yeah, and that's it. You simply end up with an empty wire between Alice and Bob, where she can just send any qubit state to Bob she wants. So this shows how quantum teleportation can be derived in the aesthetics calculus. So when I look at my time, I think it's actually what I'm gonna talk about today. So I hope I was able to convince some of you that aesthetics calculus is a really useful tool. So what was important to me in this lecture is to show that these spider diagrams are not just cute little notation, but that they fully cover everything that happens in the Hilbert space model. And I hope I could convince you of that. So that's from me. Thank you for your attention.
Wonderful. Thanks a lot, Ivica, for this amazing, amazing session. I think, yeah, broadly speaking and judging on the basis of our Discord interaction, this was one of the most, I would say, interactive sessions we have had. Like the Discord chat was pinging every second. We had technical discussions going on, but we also had a lot of fun in the chat, people sharing memes, graphics, because they really like the interpretation of quantum circuits as spiders. So yeah, that's a cool take on the entire quantum theory and quantum information theory as we know it.